Welcome to EPG Pathashala. My name is Dugirala Vasanta. I'm a professor in the Department of Linguistics at Osmania University. Today I'll be talking to you about speech perception. It is module number 6 in the Psychoneurolinguistics course. In this lecture, I will talk to you about some concepts, important concepts about how human auditory system perceives speech sounds, and about the integration of vision and audition in speech perception. Let's start with the hearing mechanism. In the diagram that you see, which I'm sure you're familiar from your school textbooks, the auditory mechanism has three main parts: the outer ear, the middle ear, and the inner ear. And each part plays a different role. I will talk about the function of each part a little later. But when sound enters through outer ear and the three small bones in the middle ear carry that sound and convey it to the inner ear. The inner ear, there is a lot of frequency and time processing takes place in the cochlea. The eighth auditory nerve takes the information from cochlea to the auditory cortex, as you can see in the next picture on cochlea to auditory cortex pathway. That is, from cochlea, the sound travels through many subcortical structures through brainstem and midbrain, and then reaches the auditory cortex, which is in the temporal lobe of both hemispheres, right and the left hemispheres. As you know, the different parts of the auditory mechanism has different functions. The outer ear helps in protection, amplification of the sound, and localization, where the sound is coming from, which direction. The middle ear does a impedance mismatch. So, it also conveys information to the vowel window connecting to the inner ear. Also, there is a lot of pressure equalization. As you know, middle ear is connected to the throat through eustachian tube. So, when you have infections of the throat, the eustachian tube does not function properly, and then you have infection in the middle ear, and that can affect your ability to hear speech. So, middle ear has impedance matching function, and it has pressure equalization function, and it also has a mechanical vibration it conveys to the inner ear. The inner ear itself does a whole lot of things happen, processes happen within the inner ear. It's mechanical and hydroelectric, electrochemical processes take place in the inner ear in transforming what we hear, the environmental sounds. By the time they reach the brain, a lot of transformations take place. And in the central auditory nervous system, the information it reaches the primary auditory area in the temporal lobe, and then it gets passed on to the Wernicke's area, which is the interpretation center. It's the Wernicke's area which attaches meaning to the sensation that we hear. So we are able to differentiate, for instance, car horn from cycle bell, or even environmental sounds. Attaching meaning to the sound happens in the Wernicke's area, which is in the temporal lobe. The main auditory cortex is the temporal lobe. So, basically, our human auditory system is very sensitive to wide range of sounds, ranging from, say, about 100 to 10,000 hertz. But today we are talking about speech perception. So, to focus on speech sounds range is not as broad. Speech sounds are spread out on the auditory spectrum from, say, about 200 to 8,000 hertz. Speech sounds also vary tremendously in terms of loudness. Some are very soft, some are very loud. Vowels are louder than consonants, right? So, basically speech perception involves converting acoustic signals which are going through our auditory mechanism to the brain, converting those auditory signals into representations in the brain. The representations are about phonemes, or about syllables, about words. They are stored in the brain. So, the speech perception is this transformation of the information that we get from the environment and making meaning out of those acoustic signals. If you see the next diagram, this is an audiogram. It's a measure of hearing sensitivity, and if you impose speech sounds, how they are spread out in this auditory spectrum, the audiogram, the horizontal axis, you can see frequencies from 125 Hertz to about 8000 Hertz. Most speech sounds are located between about 250 and 6000 Hertz or so. As you can see in the lower frequency side, you have nasals, you have vowels, and you have voiced sounds. Whereas the voiceless consonants are slightly on the higher side, and you have fricatives like s, sh are very high frequency based sounds. And in terms of energy also, vowels and nasals are much louder than the high frequency fricative sounds. So the next chart also shows you clearly the categories, the phonetic categories, which to some extent are present in many languages with some difference. So you have vowels, you have diphthongs, liquids, glides, nasals. You examine this chart, which you may have learned from phonetics class. So let's not spend more time on this. My focus in this lecture is to tell you how our brain is able to distinguish these various sounds from one another, and what one's native language, how it influences this perception, and how audition and vision come together in perceiving speech sounds. As you know from your fundamental course in physics, frequency is measured in hertz and intensity in decibels, and each speech sound has another dimension, time, that's measured in milliseconds. So we need to now understand for some of the consonants and vowels what are the frequency, intensity and time dimensions are, and that is the speech acoustics, and much of my lecture is about speech acoustics. Let us look at some spectrograms. I have already pointed out that spectrogram is a plot of frequency versus time to observe how acoustic cues such as formants, antiformants, stop gap, voice bar, aperiodic noise, how they look like. Um, so spectrogram displays the frequency information on the y-axis and time information on the x-axis. Acoustic energy is indicated using color coding. Since I am going to show you color spectrograms, you have to know that the red or the orange is indicates loudest, that is acoustic energy is maximum in the area which is marked by red, and purple is the weakest, the acoustic energy is weakest. Please remember this when you are looking at the spectrograms. Periodic vibration of vocal cords generates formants. So when the vocal cords vibrate, it's periodic, and it comes out in the spectrogram as horizontal bars, which are called formants. Nasal sounds like n and m also have formant-like structure, but if you see in the spectrogram, you see that there is not that much acoustic energy and they're weaker. You will not see red-colored antiformants associated with nasals. Aperiodic noise is associated with fricatives. So now see on the screen, you have a spectrogram showing nasal antiformants. So the word is mit. There is antiformants just before the vowel e in mit. You see there is not that much energy in the antiformants, and then you have the horizontal bars in red. So that corresponds to vowel e, which is very loud, and therefore you see red colored bars, 3 of them. And then you have stop gap. There is, because the word is ending in voiceless plosive, so there is no voice bar. It is called stop gap. And then the t, mit, is released. The plosive t is released. So this is called release burst, the last part of it. So this bottom spectrogram is a word, is a spectrogram, it corresponds to the word moss. So the acoustic cue, which I said aperiodic noise, is very clearly visible here in the rightmost side of the spectrogram, where you don't see formants at all. It is aperiodic noise it corresponds to fricative S. Fricatives and affricates produce aperiodic noise. So you can see aperiodic noise. And MOS, the vowel again is producing the formants here. So in this spectrogram, you have seen antiformants and you have seen formants. You have seen stopgap in relation to voiceless plosives. You have seen aperiodic noise which corresponds to fricatives. Then you have next spectrogram corresponds to NAB. Okay. So notice the antiformants corresponding to nasal consonant na, again very weak. Formants corresponding to the vowel a, voice bar corresponding to ba, burst corresponding to release of ba, right? But what about not many of our words also have diphthongs. So what happens when we produce a diphthong? The concentration of acoustic energy for vowels is reflected as horizontal bars, which we are calling formants, right? But when the diphthong, it's a changing quality of the vowel, right? So you see a movement in the formant. So the formants move when a word has a diphthong. For instance, a word like preempt, you see the spectrogram next. You see the formant is moving. Native speakers of English, for instance, any English word that starts with p, t and k, they pronounce it as p, t, k. We don't do that, but they do that. That's their phonological rule. So when that extra puff of air has an acoustic cue, we can show physically what happens when you aspirate a sound. Now, the acoustic cue that you have to learn, it's very important in acoustic phonetics, is called voice onset time. The time difference between the release of the plosive and the time when the vocal cords vibrate is what is known as voice onset time. This voice onset time is much longer for voiceless consonants compared to voiced consonants. So it can be measured in milliseconds, and the difference, the voice onset time differences to distinguish voiceless plosives from voiced plosives differ from language to language. They are not fixed, they differ. So voice onset time, in the next diagram that you see, the first topmost one, for instance, is the diagram which is saying there is a closure phase. Every plosive there is a closure phase when the lips are closed, pa or ba, and then if the vibration starts during the blocked, when the lips are still closed, if the vocal cords vibrate, then you generate what is known as voiced plosive, which is bha or dha or gha. These are the sounds which are like murmur. These sounds are not there in English. It makes no sense for them, for English people to understand what is bha or what is dha. But it is very important in Hindi and Telugu and many of our languages. We make a distinction between ba, bha, da, dha, gha, gha. Right? So the first diagram says voicing starts even before the release of the closion. Next level, you have voiceless unaspirated plosives. We also say pa without aspiration. Pa, palu. Palu we don't aspirate, right? So voiceless unaspirated, it's there in English also, but in certain positions, not word initial position. So in voiceless unaspirated plosives, at the time of release the voicing starts. As you can see, the quiggle is put along with the release. The third diagram is voiceless aspirated plosives. That is the p, t, k, which is very important for English, as I pointed out to you. They don't say ki, they'll say ki in English. We don't do it, but in English speaking people say p, t, ki. There is an aspiration. So that indicates that there is a lag. Even after the release, there is no voicing hasn't started. Okay, so the time difference between the release of the articulators and starting of the voice, voicing, that is vibration of the vocal cords, is what is known as voice onset time, and the brain perceives this voice onset time and differentiates different sounds. So in other words, to summarize what I have said about acoustic cues for different speech sounds, you have formants for vowels, you have antiformants for nasals, you have stop gap or voice bar for voiceless and voiced plosives, you have aperiodic noise for fricatives and affricates. These are only examples of some of the acoustic cues corresponding to different phonemes. But you must realize that each phoneme does not have one fixed acoustic cue. This is what is they are changing all the time. The acoustic cues are not fixed. Our ears and brain perceive these acoustic cues and contrast the meanings in words differently depending upon our native language. Now this is a difficult point and we need to spend some time thinking about how native language influences speech perception. Let's take an example from Hindi. Hindi makes I'm not a Hindi speaker and I may not be pronouncing the words correctly, but those of you who are Hindi speakers, you can try pronouncing them. In Hindi there is a word I believe called bal, which means hair, right? Bal is contrasted with dal. Dal is lentils, what we eat. Bal, dal. The dal is contrasted with dal. Dal is branch of a tree. Dal. And then it is contrasted with gal, which means cheek, right? So, in order to, for the brain to understand, perceive the differences in bal, dal, gal, it has to keep track of the various acoustic cues. But say dal and dal, it makes no sense for English speakers. Because the and the are not two different phonemes in English. It's only relevant for Hindi. This is the language specificity of speech perception. Hindi contrasts bhal, I believe it means knife blade, with bhal, which means forehead. So pha, bha are contrastive in Hindi. They are not contrastive in English. English, there is no bha, right? So each language has different phonemes. Each phoneme has underlying acoustic cues, and our brain receives these cues, combines them differently to make meaning differences. Ultimately, communication is not about receiving sounds. Communication is about making meaning differences in words, and that's where the language specificity comes. So, languages use acoustic cues differently to achieve contrastivity in meaning of words. Alright. So, you also know that words have clusters in them. You know, kla, samyuktaksharam. In Telugu we say that, I think it's there. Sanskrit also. Many languages allow pla, kla, bla, gla. So, like English, German, Norwegian, Thai. But all these languages don't allow tla and la. Why? It's nothing to do with the ability to pronounce. We can all say tla, we can say la, but they don't allow, right? English makes a contrast between ba and ga, pa and ka before la. So you have blue, you have glue, you have plan versus clan. You contrast, but the dla and tla are not possible, as I said, right? Take sra, s followed by r. It's totally banned in English. You open a dictionary and see, you will not find a word which starts with sa followed by ra. It's not allowed. But Telugu allows, Hindi allows, right? So these are phonotactic rules. Which sound can follow which other sound is language specific, and that knowledge we have, and that knowledge helps us to perceive clusters differently. Now, so in other words, language specific phonologies. Phonology, when we move away from sound description to combination of sounds and their function in language, we are moving from phonetics to phonology. So different languages combine their speech sounds differently. So you have English, most words are consonant, vowel, consonant. You have cat, mat, bat, whatever, right? Most words are CVC. If you take Telugu, it will be CV, CV. Gadi, Nadi, Chali, Gali, CV are more common. So that fact is again language specific. Syllable structures are, in other words, syllable structures vary across languages and we have that knowledge. There are codas, as I told you just a few minutes back, that onset and coda are two parts of a syllable. What is allowed in the onset position, what is allowed in the coda position differ across languages. Then you have various other factors involving coarticulation and assimilation in fast speech. All this influence speech perception. Maybe more about that later. So, we have talked about certain acoustic cues and how those cues participate in contrasting meaning differences. So, if you take in the spectrogram that I'm sure you will see in the on the screen, you will see burst. What is burst? Burst is a cue for plosives, right? It is followed by a transition. There is a form and transition is happening. But the way this burst and form and transition, the way they organize themselves differ for different syllables. So you can go and look for a spectrogram to see how pl is different from say cl or whatever, right? In other words, a single phonological feature like voice. I said p, t, k are voiceless, b, d, g are voiced, right? So voice is a very important universal phonetic feature. But the phonetic value of that voice can change from language to language, right? So when we say voice onset time, which I have already explained to you, the range, so the range can change across different. If you take Thai makes a difference between no aspiration, mild aspiration, heavy aspiration. So it's not matter of pa, ba or pa, pa. It is pa, pa, pa. You know, the contrastivity. So in other words, when you measure the voice onset time for pa, 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 it varies quite a bit. So brain has to keep track of this native language specific acoustic cues. So and they're changing all the time. And you can think of the complexity when one is multilingual. When a person is using English and Telugu and Hindi and various languages together, and we are sometimes mixed languages. In India, we mix languages when we are talking to a person. When we know the other person knows the two or three languages, we mix, and brain has to keep track of all that and still perceive. So basically, I'm emphasizing on the notion called invariance. That is, there is no consistently reliable acoustic cue or even a set of cues for any one phoneme. They keep changing. They change depending upon the phonetic context, whether the vowel is preceded by which consonant or followed by which consonant, or what is the onset, what is the coda allowed consonant, speaker's voice. You know that men speak at a much lower pitch than women. That is called fundamental frequency. Fundamental frequency of men is about 100 hertz lower than that of women. Fundamental frequency of small children is double the fundamental frequency of women. So we are talking about 400 hertz for children, 200 hertz for women, 100 hertz for men. That is the fundamental frequency which is influenced by the thickness of the vocal cords, the distance between glottis, that is space between the vocal cords to the lips, that entire distance, those physiological variables influence fundamental frequency. You also know that at puberty, first, if you are listening to 3 or 4-year-old children inside a room, you cannot make out how many boys, how many girls. They all speak at 400 or 380 or 450 or whatever. But at the age of 11, 12, the boy's fundamental frequency falls from 400 to 100. Whereas the girl's fundamental frequency doesn't fall that much, from 400 to 200. So You also know that at puberty, boys experience a lot of pitch breaks, high pitch, low pitch, high pitch, low pitch, and then it stabilizes, right? All that is fundamental frequency. So, men and women's spectrograms look different. The acoustic cues look different slightly based on speaker's voice. Speaking rate. Some people speak very fast, some people speak very slow. That also influences the acoustic cues. Age and gender, as I already explained. So these are all the some of the reasons for invariance in the speech signal which is reaching the brain, but brain is able to ignore all that and still perceive the meaning. Role of context. So suppose if I say, let me read one sentence. It was found that the eel was on the axle. So where I made the click, one phoneme is missing. But if I give you a cue that it is wheel, then I mean, like in the sentence, axle tells you that the click corresponds to wheel, but the same click corresponds, if the sentence had shoe, then you would hear it as heel. If the sentence has peel, I mean, if the sentence has orange, you would hear it as peel, right? The context of the sentence, even if somebody coughed or even if a car passed by and you missed one acoustic cue, this context gives you information and you say, oh, that must be heel, that must be wheel, that must be peel, right? So, context influences your perception. So let's now talk about what are the important questions research and speech perception is addressing. So the researchers are saying, are there language specific differences in categorizing sounds? So do everybody categorizes pa from ba in a similar way, ta from ga in a similar way? How do we find out what are these categorization abilities of people speaking different languages? How do children learn to categorize native and non-native speech sounds? This is very relevant in our context because we grow up learning 2 or 3 languages simultaneously. In the playground, we have to speak Hindi. At home, we speak Telugu. At work, we speak English. How do we learn? How do we learn to categorize speech sounds and keep the categories separate? What is the nature of reorganization of language-specific phoneme perception as a child grows? In other words, if I do speech perception experiments on 4-year-olds and on 20-year-olds, do they perform similarly? Is there a developmental trend in speech perception? There's a lot of research going on there. What are some of the top-down and bottom-up processes in speech perception? Top-down is how much of our knowledge about language do we bring in to understand what we heard. Bottom-up is how much attention we are paying to the acoustic cues. Bottom-up, acoustic cues to knowledge, knowledge to acoustic cues is top-down. How are these processes and how do they meet? These are some of the issues addressed by researchers. So, for that, categorical perception is one of the earliest experiments done to find out, do people categorize speech sounds similarly across different languages. So, definitely we all differentiate pa from ba, ka from ga, ta from da. Everybody, whether you are English speaker or Hindi speaker or Telugu speaker, you can differentiate. But are there differences? How how much of acoustic information do you need to identify something as pa, and is that acoustic information, does it change from native speaker to native speaker? So these are the questions that experiments on categorical perception researchers address that. So for instance, for English speakers, the phoneme boundary between ta and da is about 35 milliseconds. So you have to realize that now speech perception research has advanced to an extent that we can make synthetic speech. We don't have to, you and I cannot control the voice onset time. Therefore, you use synthetic stimuli to do this experiment on categorical perception. So, if you give to the ear a synthetic syllable with which is of about less than 30 milliseconds, all English speakers call it the, and if it is more than 40, they'll call it the. I told you voiceless has higher voice onset time, voiced plosives have lower voice onset time. But English speakers require 30 or below milliseconds to perceive it as voiced, 40 or more milliseconds to perceive as voiced, right? But this 30-40 thing is not, it doesn't remain for Spanish, from German and from Telugu. Native speakers require different amount of acoustic cues to make the same categorization. Same categorization between two sounds, you require different degrees of acoustic phonetic information. So, in addition to that, if what you are hearing is a word and not a non-word, that influences your perception. It's called lexicality effect. Because our brain is able to grasp the meaning, and therefore you can fill in the gaps. So words are perceived better than non-words. So in the diagram that we are showing you on the screen, there are two, one red line and a blue line. They represent the voice onset time experiments where, so for instance, up to a point, the red line, up to a point you hear one sound, and after that your discrimination ability falls down, right? So this is a weak form of categorical perception exists for all consonants, but vowels are classified not categorically, but it is little more continuous. So when you talk about speech perception, there is continuous speech perception, mostly it applies to vowels, categorical speech perception which applies to consonants, and categorical speech perception is not universal. The acoustic information required to categorize sounds is varies from language to language. Now, not only that, as I said that the phonological principles of a language influences your perception. How do you explain this? Let's take for instance, for both Korean and English speakers, the vowel transitions, remember the formants either go up like this or come down like this, those are the transitions. The vowel transition information is very important for both Koreans and English speakers. They signal differences in place of articulation, whether you are hearing the which is forward or ka which is back, right? Place of articulation information is signaled by formant transitions, and they are important for Koreans and English. But speech perception research has shown that Korean listeners are better able to identify consonant place information from transition stimuli alone than American listeners. Alright? In other words, that acoustic cue called formant transition is more salient in Korean than in English. This has to do with the functional load of phonological contrast among tense, slacks and aspirated stops in Korean compared to English. In other words, you have phonological categories, phonetic categories, they all have acoustic cues, but acoustic cues contribution to contrastivity varies from language to language. So, the conclusion is speech perception is language specific, alright. Speech, but I said phonology influences speech perception. Now, the other way is also possible. Speech perception influences phonology. So, for instance, there are some contrasts which are very weak to hear. Some are very strong. So, for instance, in English pluralization, if you take, when you say dishes or judges, you have a as, right? That's because it's very difficult to, naturally we come up with certain repair strategies by inserting a vowel, epenthesis it's called, so that the contrast becomes salient and perceptible. So dishes is much more easy to hear than dish. How do I put S after SH? Dish. Jet. You can't do that. So we insert a vowel. So in other words, the speech perception makes certain demands so that you come up with repair strategies. Stops never undergo place assimilation in any language unless nasals do. Nasals are weaker, they are low frequency based, so there is a implicational relationship among different consonant groups. Alright. So, because nasals have weaker acoustic cues, they are very weak. Therefore, in fast speech, we say, when we say did you, we don't say did you. We don't speak like that. We say did you. This is a j. Did you eat? Right? This is assimilation. Right? So, in other words, this assimilatory phenomena and repair strategies, all these are indication that perception also places certain demands and influences the phonology of different languages. Alright. So, in other words, you have to learn a little bit about what is the difference between assimilation and coarticulation. I have also said there is coarticulation. So, assimilation is a slightly higher level phenomena. It is a phonological phenomena. Coarticulation is more mechanical, biomechanical, lower level process. So, in order to understand this, in your module, I have given a task for you. I worked out one example. I said, when you say in peace, we don't say like that, in peace. It's actually becoming ma. It's not in peace, it's in peace. So, that's called labial assimilation. I wanted you to work out 4 more words. In vain, one thing, that car, like you. So, read up the material that is given to you. Tell me which kind of assimilation is taking place in vain, one thing, that car, and like you when you say it fast. I will not give you the answers, but you try and work it out. So, now the question is auditory perception different from speech perception? So far I have been telling you only about perceiving speech sounds. What about our ability to perceive all kinds of environmental sounds? So, in what way is auditory perception different from speech perception? So, many years ago, I think in the 70s, they did an experiment called duplex perception. What they did was, they took a syllable, CV syllable, they fractured that into 2 portions. One is form and transition. It's a clear-cut acoustic cue in isolation, right? So, when you take only form and transition synthetic stimuli and give it to your ear, it sounds like ch, some chirp, right? It has no meaning. It has no meaning. But if you say pa or ta, in some languages ta means give. It can have some meaning. So, when you attach the steady state portion of the vowel along with the form and transition, then it is more meaningful. So, what they wanted to know is what mechanism is playing a role in hearing and perceiving ch as opposed to cha, right. So, you look at the spectrogram we are showing you on the screen. The circle shows transition of the third formant alone given to the left ear, and then everything else is presented to the right ear. That is transition plus the formant which contains the vowel information. The entire information is given to the right ear, and left ear is receiving only the formant transition which sounds like ch, ch or whatever. So, I believe listeners heard both. So, what does it mean? What sense to make about duplex perception? What the researchers are saying is, there is an auditory mode of perception for environmental sounds which brain receives from both the ears, integrates it and makes sense of it. But there is a phonetic mode which is language specific, and that information is processed better from the right ear. Why right ear? From right ear, it goes straight to the left hemisphere. In majority of the people, speech and language is understood and processed by the left hemisphere. So, the right hemisphere receiving all the information is processed like speech, made sense of like language. So, that mechanism is there. At the same time, we can also hear like that, those sounds. So, this is what is called duplex perception. Both categorical perception and duplex perception are cited as evidence that speech is a special module present only in human beings and at birth, right? So, both these experiments are endorsing modularity, alright. Now, okay, so far what we said, to recapitulate, we are saying acoustic cues are important, but there is no one acoustic cue underlying each phoneme. Acoustic cues combine differently to make meaning differences. Contrastivity, language specific contrastivity is produced by different combination of acoustic cues which the brain is able to perceive. There is some amount of information coming from auditory perception, but a special speech module must be present in the left hemisphere, which is capable of processing language specific speech information from speech sounds. That is a phonetic module. Speech is special is the argument so far. But there is also phonotactic constraints which influence speech perception. There is perceptual assimilation. You may have heard that Japanese listeners and speakers, they don't make a distinction between r and l. To them, when somebody is saying r and l, they have only one percept, right? It's perceived as r. But when presented with so what happens when they hear drama? When Japanese people hear drama, they report hearing the do ra ma. They insert do. The da and ra cannot come together in Japanese. So, what did you hear? Drama, do rama. They will even pronounce it as do rama, they hear it as do rama. In other words, the listener perceives illusory phonemes. Phonemes which don't exist are perceived because your language forces you to listen according to the principles of your language, which are relevant to your language, right? So, they are able to now talk about, there is a phenomena called McGurk effect. It's very interesting, and on the screen you will see a website. If you go on the website, they will actually give you a demonstration of how this McGurk effect works. Basically, it is named after Harry McGurk. When you are made to listen auditorily ba, at the same time you are forced to look at the lips which are saying ga, you report hearing da, alright. So, in other words, what happening, magnitude of this effect is influenced by competence in lip reading, of course, and also listening conditions. If there is a lot of noise, you will pay more attention to the lips. So, you first look at the website, have a demonstration, but what is the explanation for this McGurk effect? Vision plays a role in the perception of differences in place of articulation. Audible speech determines you need audition for differentiating voiced from voiceless. If I say pa, ba, you can't say anything on the lips. You have to hear it. Audition plays a greater role in differentiating voicing. The vision plays a greater role in differentiating place of articulation. And when there is a clash, the brain gets confused. The two modalities get fused and support perception, resulting in the or gar, whatever. The brain tries to find the most likely stimulus given the conflicting cues. When there is a conflict between vision and audition, it just settles for the most likely one, right? In other words, maybe the audiovisual integration is taking place pre-lexical stage. That is, even before you reach the mental lexicon, this confusion is happening and brain somehow. So, this brings me to the summary of my lecture today. There are just 4 or 5 points. I will just repeat that. There is considerable variability among acoustic cues that underlie perception of different speech sounds. That is, there is no one acoustic cue relating to one phoneme and the other way around also. You can have one phoneme with many acoustic cues, or you can have one acoustic cue for many phonemes. So, there is a lot of variability. Categorical perception and duplex perception support motor theory of speech perception by holding that there is a close relationship between speech production and speech perception. Alright. Perception of language specific phonemic categories is influenced by lexical knowledge, knowledge about words, our mental dictionary. What we know about words influences the way we perceive phonemes also. And it is language specific. Both auditory and visual modalities contribute to speech perception and the degree to which we understand the intended message. And I only dealt in this lecture, I only talked about how the focus was on speech sounds. But in real life, we don't hear individual sounds. We have to move into words. And the next next module deals with word recognition. I hope the main gist of what I have tried conveying to you, you have understood. Do consult the e-text as well as additional reading material we have mentioned in the e-text, which will help you to clarify some of the points. Thank you.